This is part 2 of an instructional video on how to use AirTest CO2 Demand Control Ventilation Energy Analysis Program. Let's get started. Okay, so then we have the building characteristics set up. The next step is to really set the parameters for heating and cooling. Now you can see there's a lot of blue boxes here, and this is because this is just the way things are set up. Generally, you won't have to choose these. Now, as I said in the earlier presentation, since we aren't doing an internal thermal analysis of the building, what we have to do is use what I call a heat balance method, where we have to say, all right, in this program we're going to assume that, as we see in one here, we're going to be in heating mode from the lowest temperature that's recorded outside to 50 degrees F. And then from just above 50 degrees F to 55, we're going to say the building's in a neutral condition, where it really doesn't need any heating or cooling. And then when it's above 55 to whatever the highest temperature is outside, it's going to need cooling. So then for the outside air economizer, we talked about having some options. We have to set the operating parameters for these. First, we have temperature-only economizer that really operates from 55 to 68 degrees. A dew point and temp economizer, which is what we're really advocating people use now, which would be at 68 degrees, and as long as the dew point was below 55 degrees. And then the enthalpy economizer, which typically, for example, here in California, they recommend a level of 29 BTUs per pound. And I also set an upper temperature limit of 68 degrees on that. So these are the parameters at which the economizers will click into space. And the final report actually reports on all three of these, so you don't have to make a selection. In terms of design conditions, basically here we're assuming outside air coming into the building is heated to 68 degrees. The indoor cooling design temperature is 72, though in the calculations itself that really doesn't affect very much. For the indoor moisture level, I have a target of 55 degrees dew point, and when you type this in, it will tell you what the relative humidity condition of this is at whatever the set point is. So in this case, if we control to 55 degrees dew point, it's equal to 55% RH at 72 degrees F. So a reasonable humidity in the space. And then when outside air is brought in, really to be cooled down, it moves through a cooling coil, which in this case we're assuming is 55 degrees. And of course, when you cool it to 55 degrees, you bring the dew point to 55 degrees. So that's why those two are equal. And generally, if you're adjusting this number, you should try and make them equal. Okay, so then basically we input the heating fuel info, which includes for natural gas the cost per therm, and the heating efficiency, which in this case I've made 75%. You can type in what kind of cooling you have here, and then basically type in the electrical rate and then the kilowatt per ton efficiency. If you're not familiar with kilowatt per ton, underneath we also show the COP or the EER. So you can adjust the kilowatt per ton to actually reflect whatever term you're more familiar with. So for example, if I make that 1.2, you'll see that it changes the EER down to 10. Oops. Okay. So I'll make that one again. Okay, so that's third step. Fourth step is we have to actually pick a climate location. And so for this, we actually click on this menu, and you can see that we have a number of choices to choose from. Let's see, what will I, oh, it seems to like to pick Abilene. Let's go to Birmingham, Alabama, okay? So once we pick the city, then in this case, if there's days that the system isn't operating and it looks at kind of a 7-day schedule, you can put those days in. For this simulation, we're going to say, no, it's a store, it's operating 7 days a week. 5 days a week are weekdays, though, and during those weekdays, it's sort of a lesser occupancy than it is on weekends. So we've got a Schedule 1 with 5 days and a Schedule 2 with 2 days. Also, what we've done is we've set up so that in adjusting the time, people come in at 8 a.m., let's say, and store opens at 9, and it actually stays open till 11 p.m., let's say. You can actually do a full 24-hour schedule if you want with this. Okay, so we got 8 a.m. and then take it to 11 p.m. again. Okay, as you can see here, if there's certain months you want to exclude out of the analysis for one reason or another, for example, a school might have a couple of months where it's not operating, you can decheck the boxes here, and that month will be discounted from the analysis. Could also be that certain times of the year there's a drastically different occupancy pattern, and you want to omit that from your first step in the energy analysis, but then come back and only include those months you omitted in the second one, and then you'll just have to add things together. So then once you do that, we have a table here that actually allows you to put in the hour-by-hour occupancy. And basically what you should do is have an occupancy inputted here for basically all the time that the space is occupied. So here it's giving me an error which says, hey, listen, the space isn't occupied right now. Let's make it 0. And this table changes. This black part says no occupancy. This says yes, no, yes. So then what we're saying is for most of the time the building is, during the week, is at only about a 20% occupancy, except perhaps in the evening when people come in to get their prescriptions and everything. So we're going to make it 30%. Oh, that's 39. 30. And you can put in whatever numbers you want. So again, our design occupancy up at the top here is 260 people. And then on the weekends here, we're going to adjust it so that initially it's 20%. And let's say it goes up to 30% for a couple of hours and 40%. Back down to 20. And again, you put in whatever hours you want. Basically then what happens is, as you can see here, we put in a certain occupancy here, but our default minimum design ventilation rate is here. So when we calculate the amount of air from our base case, which is really ventilating 24 hours a day for 260 people, versus this occupancy, we see we're really only going to provide about 23% of the average ventilation for the space for Schedule 1 and 27% of the ventilation for Schedule 2. So once you do that, then just hit this run button, which actually goes to the city climate that you selected and does all the calculations on it. So we have the location and schedule, and then it's just a matter of looking at the results. And here, basically, we have a presentation of the many of the important assumptions into the program, and then you can compare two different variables. So for example, here if we want to compare gas heating and cooling with no economizer, with gas, let's go with cooling with a enthalpy and dew point economizer. You can see in this case that here's the heating cost that we're going to incur for the base case is the first line, and then the second cost is the CO2 case, and the savings are shown below. So basically what we're seeing here based on the inputs we put in here is that our heating costs are going to be about $341, or savings with CO2 are going to be about $341, and the cooling cost savings is going to be around $6,233, giving us a total annual cost of $6,000, which actually will save us on an annual basis 64,000 pounds of CO2 greenhouse gases a year. The other thing is that I've included in this is a sensitivity analysis, because we do know that buildings tend to be ventilated over their design ventilation rate, and there's actually an EPA study that addressed that, and we've written a little white paper that talks about that. At any rate, if you want to just do some sensitivity analysis and say, hey, what if the space was overventilated by 20 CFM or 5 CFM per person? So rather than 15, it was 25 CFM. you can play around with this number to get a number here that you want that will then tell you what the impact on savings is. And you can see for ventilating, just if that damper, initial damper position is 5 CFM per person more open in the space, the savings go from 6,574 to 9,623, almost 1/3 more savings from CO2 if that damper is improperly set. So we have worked with a few utilities who are using this as a basis for calculating rebates, and what they do is they just assume some number over design is present in the building, and they'll base their energy savings analysis based on that. So that gives you a good idea of what the energy savings are. It's fairly straightforward, and again, you can look at different scenarios if you want. Finally, there's a final tab which just takes a look at the use of CO2 and economizer operations. Number one, the first chart just looks at, all right, what are the savings due to just the economizer? And we look at a dew point economizer, temperature only, or enthalpy. If you're not using an economizer, don't even bother looking at this. You can see with the dew point and temperature economizer, there's much less operating hours because basically the economizer doesn't operate when moisture levels are above those outside design conditions. This shows the operation for the temperature only and enthalpy, which are somewhat close. And you can see that for the percentage of hours where the outside air is actually over the design dew point, it's quite significant. So they're bringing in a lot of moisture. If we take a look at then how much savings in kilowatt hours is happening because of free cooling going on, temperature cooling, these are the numbers here. But if we take a look at what's the cost of bringing in that extra moisture, because once we bring it into the space, we actually have to dehumidify that once the air conditioner goes on. So we basically take a look at the savings kilowatts, subtract the penalty for dehumidifying the space, and this gives us our net savings. And you can see here then, if we take a look, the dew point and temperature is a little bit less, but we don't go through this whole effort of bringing moisture into the space and having to dehumidify it. Of course, the other thing is about enthalpy. We're assuming we have an accurate enthalpy sensor here, which is very unlikely unless you go to a very extremely expensive device that requires high levels of maintenance. Again, we can look at the total savings for the economizer and the CO2 in thousands of dollars, and or I'm sorry, just for the economizer, and then the annual greenhouse gas savings. Then when we add in CO2 and economizer, you can see exactly basically the same parameters and what potentially we can save. So that's the program. One other thing, if you want to create your own custom report, there's one other tab here that's unlocked where you can actually copy in values, or you take a cell, I want this cell to equal this number here, and you can basically build your own report customized with your logo, whatever you want to show that to do your own custom reporting. So that's the program. Hopefully you found this training useful, and as always, when you get the program, my contact information is on the first page, and you can write me an email or send me a note if you have any questions. Thanks. Bye-bye.